Hi everybody, and welcome to what is personally my favorite topic, which is all about the fundamentals of mixing. And we're going to begin with a general discussion of the concept before diving into the details of exactly how it works. And I'd like to start with a video showing a mixing process in order for us to give a scientific definition to mixing in the context of a fluid. You probably have a sense of how you would describe mixing in terms of usage for your everyday life, but you might not be able to scientifically say exactly what it is. And this video is one of many that I'm going to be sharing from the National Committee for Fluid Mechanics. They're several decades old, but they're really good visual examples for some of the phenomenon that we'll be talking about throughout the lecture on mixing. So in this particular clip, you can see dye being dropped into a tub of water, and then it is being stirred vigorously, and this dye is being distributed across the entirety of this water. So initially there's a clear distinction between the dye and the water, and eventually there's no more distinction left. And so based on what we're seeing in that video, what we can perhaps say about mixing is that this is a process that is reducing differences across different regions of a fluid. So initially we have a very high concentrated region of dye in the middle of this basin, and regions where there is almost no dye whatsoever, and eventually, by the end of this process, there are no differences in the concentrations and everything is uniformly distributed. So the fluid is becoming more homogeneous over time. Examples of this that you might have seen in your everyday life are, of course, stirring cream into coffee, or even for granular mixtures and non-fluid mixtures, you can think about stirring in terms of things like baking. So it's all about a time process that is removing differences that you see across different spatial regions of a fluid. For the purposes of our lecture, we're going to simplify things down to one direction. So we will neglect any mixing that is happening horizontally and instead look at what's happening across a depth below a water surface. So in this representation, we have a continuous change in some quantity with changing depth, and then we can also represent it discretely just to help visualize the concept. And a discrete representation of this same scenario is that you have a large quantity on top of a smaller quantity. And over time, the mixing process is going to reduce the differences that you see across different depths. So the color difference indicating the difference in the quantity is getting weaker over time. And eventually what happens is that you have a uniform distribution of some quantity. So there are no longer any differences throughout different depths of the fluid. And this quantity, this general quantity I'm giving variable x, can represent anything that is per unit of volume. So examples of this that are relevant for fluids include your momentum or velocity, the concentration, for instance, concentration of anything including dissolved oxygen, or the temperature of the fluid, which is a representation of the heat, and corresponding to the temperature, you have the density as well. And of course, you can come up with many different other variables that can be represented by x. Mixing is always going to move quantities of this variable x from regions where it's higher to regions where it's lower. This is true in a net or average sense and maybe not necessarily instantaneously, but on an overall average, you're always going to get quantities from this region where it's higher moving to where it's lower, and due to this movement over time, you're actually going to get that the differences are becoming less and less, and eventually there are no remaining differences anymore, and everything is fully mixed or uniform. Because you're always moving from higher to lower, the movement is always opposite to the direction of the gradient. So the quantity is increasing as you approach the surface, so the direction that you're moving is always going to be in the opposite direction, which is known as down gradient. In order to quantify how this mixing is happening and how quickly it's occurring over time, what we need to do is define this net movement of x that is happening. In order to consider this net movement, we need to introduce the concept of a flux. So a flux is the rate at which a quantity is crossing a plane per unit area of that plane. So visually at the bottom, if you consider all of these black arrows that are around a plane of area A, the entirety of all of these black arrows contributes to this equation that I'm giving here at the bottom, which is the quantity that is moving from region 0 to region 1 across a given duration of time. We can consider this per unit area by, instead of looking at all of the black arrows, just consider one of them, in particular this red arrow, and the flux at that point is going to be this quantity per duration of time per unit area of this plane across which the mixing is occurring. So the change in the quantity that is happening in a finite layer that has a volume given by the planar area that we talked about already and some sort of a finite thickness delta Z is going to follow a simple law of conservation, very similar to conservation of mass or conservation of energy, where the amount of X that is building up within this region 1 is going to be based on the difference between the quantity that's coming in versus the quantity that's coming out. So the quantity that's coming in, we can use the same definition from the previous slide, where it's equal to the flux multiplied by the area. And then the quantity that's coming out from region 1 into a separate region below is going to be given by that same exact formula. If we take the difference between these two, so the flux in minus the flux out, now what is represented on the left-hand side here is the change in the stored quantity over a fixed duration of time, and that's going to be equal to the difference in the flux that's coming in versus the flux that's going out. Here I am showing the same equation from the previous slide, just so we have more space to continue with our derivation. And what we can do now is replace these words with actual variables. So quantity is equal to X, which is the quantity per unit volume, if you recall. And so in order to get the overall quantity, we need to multiply X by the volume that is represented in our discrete model over here on the right. And then the time can simply be represented using the variable T. This here, flux in minus flux out, is the negative of the difference in the flux. So the difference in the flux is going to be flux out minus flux in. So we're just flipping that and you get the negative of it. Now we have a volume on the left, which is equal to the area multiplied by the thickness, the finite thickness of our depth. And then you also have an area on the right-hand side. So the areas cancel out, and you can also move this delta Z that appears from the volume over to the denominator on the left-hand side. And what you can do now is take all of these discrete differences and consider infinitesimally small changes in time and infinitesimally small thicknesses for your layers. And in the limit of those infinitesimal quantities, what is going to happen is that this discrete representation is going to become a continuous representation using derivatives. So we have a change in X over time is equal to how the flux is changing over the depth. So the amount of the quantity that's being stored at a given position is going to be related to how the flux in is different from the flux coming out. So this equation here is simply a mathematical representation of this conservation equation that I'm showing here at the top. And the partial here is simply the partial derivative of the flux with respect to Z, because it varies both with Z and with time. And X, this big D, is a special type of derivative that we're going to give a definition to later on in the lecture. So with all of that in mind, what I'm going to do now is summarize the fundamentals of mixing in a single slide such that it provides us a basis moving forward. So what we have is a fluid with a quantity in it that is varying in one direction. In this particular case, we're using the depth below the surface Z. And this quantity is some general representation X that can represent anything from temperature to concentration. The goal that we have is to determine how this difference in the quantity over depth is going to vary in time, and specifically how this gradient is going to weaken through a mixing process and eventually lead to uniform or full mixing. The inputs that go into our calculations are going to be the properties of the water or the fluid and the initial conditions. So essentially at the start, what is the difference in quantity across all of the depths? And then the factors that are going to determine the exact nature by which this mixing occurs is how do we define these fluxes from the previous slide. These fluxes can be due to a number of different mechanisms. They can be at the micro scale or at the molecular scale, or they can be at the macro scale. Examples of the macro scale include the rod that you saw in the video at the beginning, where that rod is providing stirring that enhances the mixing, or it can be something that naturally occurs within a fluid, such as turbulence. And what we'll do in the next couple of videos is discuss how we quantify the fluxes that are due to some of these different processes.